Alright, so the middle section of section 3.4 is essentially the same as the first, and it's essentially the same as the last, except each of the problems in the middle sections are fractions. And when you graph fractions, often you have vertical asymptotes and horizontal asymptotes. And every one of the problems that we're going to do between 13 and 20 has both a vertical and a horizontal asymptote that we'll have to worry about. I'll just jump into these problems, and basically everything's going to be a repeat of the first group of problems, and we'll just see how it goes. So as I try to do problem 14, the first thing I combine together is finding the domain and the vertical asymptotes, because there's one computation that will give you both answers simultaneously. So I gave you a function f of x equals 2 over x minus 3, and simultaneously I'm going to find the domain and the vertical asymptotes because they require the same computation. To find the domain of a fraction, we ignore the numerator and we set the denominator equal to 0 and solve for x. When the value for x is the number that needs to be excluded from the domain, and it will be fine on the test if you just use the word version of the domain. You could say the domain is all real numbers except x equal to 3. That would be completely fine. Or what would probably be better if you show the interval equivalent of this, which would be the interval between negative infinity and 3, and then the interval from 3 to infinity. You essentially block out the number that excluded from the domain into two separate intervals with all round parentheses. It means the same thing. Again, my videos get so long. If I start reteaching a lot of college algebra, they get too long. So if you're happy with that, you can just write that for the domain. So the solution to finding the domain is going to give me either the position, the x coordinate of a hole, or the vertical asymptote. X equals 3 would be a hole as opposed to a vertical asymptote if you could factor the numerator, and the numerator would have a factor of x minus 3. So if it were possible to factor and cancel to make the denominator go away, or the factor in the denominator that caused this x equal to 3, then you would get a hole. There aren't any problems in this section that have holes. Every value of x that we exclude from the domain is going to be in our graphs of vertical asymptote. We do, and there's enough going on. I don't want to compound the difficulty. So for our purposes, in each of the problems between 13 and 20, you set the denominator equal to 0. That gives me the number or numbers that I exclude from the domain, and it gives me the equation of my vertical asymptote. So that's the first feature I can show on my graph. So I'm not exactly sure what the graph is going to look like ahead of time. So I'm going to make just a big old graph with an x and the y-axis. And the first thing I'm going to do is draw a dashed vertical line through 3 on the x-axis, because a vertical asymptote is a imaginary line that we usually draw in as a dashed vertical line that the graph will neither cross nor touch. And on either side of the vertical asymptote, the graph will either go up to positive infinity or it will go down to negative infinity. So that's the beginning of problem 14, but that's what part A is going to show up like on our graph. Part B wants me to find an x-intercept. And to find an x-intercept of a fraction, it's enough just to set the numerator equal to 0. So for part B, for the x-intercept, for a fraction, the x-intercept can be found by setting the numerator equal to 0. You can actually set the whole equation equal to 0. If you set the whole equation equal to 0, you can cross multiply by making this 0, 0 over 1. And when you cross multiply, you'd get 2 times 1 equals 0 times x minus 3, which would give me 2 equal to 0. And that's the same as just setting the numerator equal to 0. So it works generally to find an x-intercept, you take the entire equation or the function and set it equal to 0. But for a fraction, the math will always boil down to setting the numerator equal to 0. And because the numerator doesn't have an x and 2 doesn't equal to 0, there's going to be no x-intercept. So there's going to be nothing extra to show on my graph for this particular step. So for each of the fractions, I'm going to find the x-intercept by simply taking the numerator and setting it equal to 0. For the y-intercept, you just plug 0 in for x. The original function is f of x equals 2 over x minus 3. To get the y-intercept, I'm just going to take the x's and plug in 0. So I'm going to do f of 0 equals 2 over 0 minus 3. And that's going to give me 2 over negative 3. And I'm going to rewrite that as negative 2/3. The answer for 14C, the y-intercept, is going to have a negative 2/3 in the y-coordinate because it's I'm solving for the y in the y-intercept. And always an intercept has a 0 for the other coordinate. A y-intercept is going to have a 0 for the x-coordinate. I'm going to plot this on my graph. Negative 2/3 is somewhere between 0 and negative 1, and this point is on the y-axis. So when I go to plot this point, the point 0, negative 2/3, I need to mark negative 1 on the y-axis, and then the point 0, negative 2/3 is between the origin and that negative 1 that I marked. And so there's my y-intercept. The graph has to go through that y-intercept. That says 0, negative 2/3. Hardly looks like it, but I like trying to show these with different colors so that my graphs are, I don't know, I like multiple colors, but if you can't read that, that says the point 0, negative 2/3. All right, so done with this sheet of paper because I'm kind of out of room there. And now I'm moving on to part D, the horizontal asymptote. And for a fraction, it's enough to just find the limit as x goes to infinity to get the horizontal asymptote. Technically, you should do 2 limits, and I'll show you technically what you're supposed to do, but it's enough to do this. So to find a horizontal asymptote, you're supposed to actually find 2 limits. So the original function is f of x equals 2x minus 3, 2 over x minus 3. I'm technically supposed to find the limit as x approaches positive infinity of the function 2 over x minus 3, and I'm supposed to find the limit as x approaches negative infinity of the fraction 2 over x minus 3. It turns out that these limits are always going to be the same number, so we can get by doing just one computation. Remember from chapter 1, to find this limit, I'm going to multiply every term by 1 over the highest power of x. So in both of these limits, I'm multiplying each and every term by 1 over x. And in the numerator here, 2 times 1 over x, you just multiply the 2 and the 1 together, and you'll get a 2 over x. In the denominator here, the x's cancel, I'm left with a 1. And then there I multiply the 3 and the 1, I'm left with a 3 over x. In both of these, the algebra is going to be exactly the same until we go to plug the number in. Now on the left one, I'm going to plug positive infinity in, and the right one, I'm going to plug negative infinity in. It turns out that a number over positive infinity or a number over negative infinity are both equal to 0. Oh, I should probably stop writing the limit now because I plug the infinity in. So when you plug the infinity in, you've actually taken the limit. So you stop writing the word limit. So on the left one, I change the x's to positive infinity. On the right one, I change the x's to negative infinity. And regardless, 2 over infinity and 2 over negative infinity are both equal to 0. Negative 3 over infinity or negative 3 over negative infinity are both equal to 0. So here I'm going to get 0 over 1 minus 0. And here, I'm going to get 0 over 1 minus 0. Both of these give exactly the same number. This is why I say for our fractions, we're just going to do this one because both sides are going to come out the same. They both come out to 0 over 1, and 0 over 1 is equal to 0. Horizontal asymptotes always have an equation with only a y. So my answer to part D of number 14, the equation of my horizontal asymptote is y equal to 0. So I'm going to find 0 on the y-axis and draw a dashed horizontal line to finish up part D on my graph. So on my graph for part D, 0 on the y-axis is right at the origin. So I'm going to draw my horizontal asymptote, but it's actually y equal to 0 is the equation of the x-axis. Graphs will never cross vertical asymptotes, but they can cross a horizontal asymptote kind of once, I think. I don't know if they can cross a horizontal asymptote more than once. And generally, more often than not, they don't cross a horizontal asymptote, but they can. All right, so now we're into just old school stuff. The next part's E, F, and G, the intervals where the graph is increasing, decreasing, and the relative maximums and minimums. So I need a first derivative for that. So as I go down to do part D, for the intervals, or interval increasing, in part E, the interval decreasing. I'm just going to start using arrows for those rather than writing the words. In part F, the maximums and the minimums, those all require the first derivative. So the original function for part, this is part E, it's D through F. My original function is f of x equals 2 over x minus 3. Because the numerator doesn't have any x's, I can avoid the quotient rule and use the chain rule, and it's easier to use the chain rule. And I'm going to rewrite the problem to take the derivative using the chain rule. I'm going to think of the original problem as the entire denominator being in a parentheses with an exponent of 1. I'm going to rewrite the problem without a fraction and with a negative exponent. So that's the original problem written so I don't have to use the quotient rule. And now I'm going to use the chain rule. And I'm going to write f prime of x right now because I'm taking the derivative. I'm going to multiply the exponent negative 1 by the coefficient 2. I'm going to leave myself some room. And then I'm going to take my original parentheses and lower the exponent by 1 to negative 2. Where I left that room, I put the derivative of the inside of the parentheses. The derivative of negative 3 is 0. The derivative of x is 1. So that's my derivative. I'm going to multiply these three numbers together and leave them in a numerator. I'm going to move this down to a denominator of a fraction. So I'm going to get f prime of x equals negative 2 over x minus 3 squared. And now I'm in a position where I can find critical numbers. For a fraction, you find critical numbers by taking the numerator and setting it equal to 0, and you take the denominator and set it equal to 0. The numerator can never equal to 0 because it doesn't have an x. For the denominator, it's just enough to take the x minus 3 and set it equal to 0. If I wrote the denominator without an exponent, I'd get 2 factors of x minus 3, and I can set each one equal to 0, and they both give me x equal to 3. So the only critical number is x equal to 3, and magically, that's where my vertical asymptote is. You're always going to get a critical number where a vertical asymptote is. You can't have a maximum or minimum there because the function doesn't exist there. So let me go ahead and do my number line work. So on my number line, I'm going to put negative infinity, positive infinity, and 3. I'm going to create my intervals. My intervals go from negative infinity to 3, and then 3 to infinity. I need test numbers. The first interval, I'm going to test x equal to 0. Second interval, I'm going to test x equal to 4. I need to find f prime of 0 and f prime of 4. And I've been doing that using the dy dx feature on my calculator. So I'm going to do dy dx 0, dy dx 4. And in order to do that, I have to have the original function on my calculator. So I'm going to enter this into y1, graph it, not play with the window so much, then do dy dx 0, dy dx 4, and see if I get a positive or negative number. So I'm going to enter the function just how it was given to me. So y equals, clear this out, 2 divided by parentheses x minus 3. I'm just going to do a zoom standard window for now. We can kind of see the whole graph. That's probably good. Now I'm going to do second calc, go down to number 6 dy dx, type in 0, and hit enter, and I get negative 0.22. So negative 0.22. That means in the first interval, the graph is decreasing. For the second interval, I'm going to do f prime of 4. So second calc, dy dx, type in 4, and I'll get negative 2.0. I'll just say negative 2. And so it's also decreasing in that interval. So the graph decreases, then decreases. The graph never changes from increasing to decreasing, so you can't get a maximum or a minimum, because you only get maximums and minimums where you change from increasing to decreasing or decreasing to increasing. So now I could answer D, E, and F. For intervals increasing, it's never. For intervals decreasing, it's from negative infinity to 3, and then union, 3 to infinity. And for the maximums and the mins, there are nones of those. There isn't really anything to put on the graph just yet, so I'll keep going. And the keeping going is just filling up the rest of the information, finding out the intervals where the graph was concave up, concave down, and any inflection points. So that's I, J, H, I, and J. So for H, it's where the graph is concave up. I, it's where the graph is concave down. And J are the inflection points. The original function is f of x is 2 over x minus 3. The derivative of the original function is negative 2 over x minus 3 squared. I want to do the second derivative for concavity, and because it's a fraction and there isn't an x in the numerator, I'm going to rewrite the problem so I don't need to use the quotient rule. I'm going to rewrite it as negative 2 times x minus 3 to the negative 2 power. Now I can use the chain rule. So I'm going to go f double prime of x. I'm going to take the exponent negative 2, multiply by the negative 2 that's already there, leave myself some room, and then lower the exponent by 1 to negative 3. Where I left myself some room, I'm going to write the derivative of that parentheses. The derivative of x is 1, the derivative of minus 3 is 0, so that just has a derivative of 1. I'm going to multiply these three numbers, put this in the denominator of a fraction. I get f double prime of x equals 4 over x minus 3 cubed. Now I'm going to find my critical numbers, and for any fraction, you find your critical numbers by taking the numerator and the denominator, setting them equal to 0. So I'm going to go 4 equal to 0, which there's no solution because there's no x, and x minus 3 cubed equal to 0. When you have an exponent equal to 0, it's just enough to drop the exponent and set the inside of the parentheses equal to 0. I'm getting that same x equal to 3. So now I'm going to plot those numbers on a number line. So on a number line, I'm going to have negative infinity, positive 3. The intervals I'm going to get are negative infinity to 3, 3 to infinity, I need test numbers. This one I'm going to do x equal to 0 because it goes from negative to positive. This one I'm going to do x equal to 4. And what I'm going to do is plug those numbers into the second derivative. So I'm going to go 4 over 0 minus 3 cubed for the 0. And I'm going to do 4 over 4 minus 3 cubed for the 4. And that I'm going to do from the main screen on my calculator. I can't do it from the graph screen. So second quit. First one I do 4 divided by parentheses 0 minus 3 up arrow 3. And I get negative 0.14 or negative 0.15, which means the graph is concave down in that interval because I got a negative. For the next one I go 4 divided by parentheses 4 minus 3 up arrow cubed minus 3, and I get 4, which is a positive number, so in that interval the graph is concave up. So to finish up my answers, the graph is concave up between 3 and infinity, the graph is concave down between negative infinity and 3, and usually when a graph changes concavity you get an inflection point, but the graph and the inflection point would have an x-coordinate of 3. But there's a vertical asymptote at 3. There's no point that has an x-coordinate of 3. So there's going to be no inflection point. Because if you try to plug 3 into the original function, you'd go 2 over 3 minus 3. You'd get 2 over 0. And you'd get undefined for the y-coordinate. And that doesn't work. So I've answered everything. I don't have a heck of a lot on my graph. And quite honestly, if I didn't have a graphing calculator with the information that I got, I wouldn't get the best graph. And I'm going to kind of fudge from my calculator. So let me just emphasize the answers that we have. We have that it's decreasing from negative infinity to 3. It's decreasing from 3 to infinity. It's concave down from negative infinity to 3, and it's concave up from 3 to infinity. And I'm going to borrow from my calculator. The only thing I need to do is make sure my graph is drawn to the asymptotes and goes through the intercepts. So this first region, this region between negative infinity and 3, the graph needs to be decreasing, concave down. It needs to be drawn to this asymptote and drawn to that asymptote. And how that looks, it goes through the y-intercept, and it gets drawn to the asymptote and goes down forever. And off to the left, it goes and gets drawn to the horizontal asymptote. So it's the horizontal and vertical asymptotes are kind of like magnets. And then in the next quadrant, it's decreasing and concave up. It's drawn to this asymptote, and it's drawn to that asymptote. And what I really did is I had my calculator handy, and I just kind of copied my calculator's work, but it works perfectly because in this interval from 3 to infinity, this graph is both decreasing and concave up. It's drawn to the vertical asymptote, and it's drawn to the horizontal asymptote, so that's perfect for the answer to problem 14. So now you need to make a crack at number 13 and do all the same parts. And pause the video, do it, and I'll do 16 next. 16's a little harder because it has an x in the numerator. So first thing, I want the domain and the vertical asymptote. So for part A, for 16a, I'm going to figure out the domain and the vertical asymptote. The algebra for these are the same. That's why I included it in just one question. You set the denominator equal to 0. That gives you the number to exclude from the domain. And as long as you couldn't factor and cancel out the x plus 5, you also get the vertical asymptote. For the domain, I can say it's all real numbers except negative 5. Or if I want to write it as an interval, when you're just excluding one number, you take that number and put it in intervals that have positive and negative infinity, all round brackets, and that would be the interval notation. So that's the answer to part A, and I can immediately throw that on my graph as a dashed vertical line. So on my graph, at x equal -5, I'm going to draw a dashed vertical line. So right through -5 on the x-axis. So I always draw vertical lines dashed for the asymptotes, even though my calculator doesn't show them. All right, so that's A done. Kind of a 2 for 1. Now I move on to part B, finding the x-intercepts. To find the x-intercept of a fraction, it's enough just to take the numerator and set it equal to 0. When I take the numerator and set it equal to 0, I get x equal to -1. On my graph, that's going to be the point -1, 0. So now I'm going to graph that on my graph, because my graph has to go through the x-intercept. Here's the point, -1, 0. Next step is to find the y-intercept. To find a y-intercept, you plug 0 in for x. So the y-intercept is going to be f of 0 equals 0 plus 1 over 0 plus 5. That gives me 1/5. And the answer for the y-intercept is the point 0, 1/5. That's just above the origin. So it's on the y-axis and just above the origin. I'm going to plot that point. So the point 0, 1/5, I'm going to call it right there, just almost on the origin. Alright, so now I'm to the horizontal asymptote. So the horizontal asymptote, we technically need to do a limit as we go to positive and negative infinity, but it's enough to do just the positive infinity. So for 16D, it's the horizontal asymptote. I'm going to do the limit as x goes to infinity of the fraction x plus 1 over x plus 5. Just like I did in the last problem, I'm going to multiply each term by 1 over x. The terms that have the x's are going to cancel out to be 1, and the other ones are going to become fractions. So I'm going to get the limit as x goes to infinity. Here the x's cancel, I'm left with a 1. Nothing cancels there, I'm left with a plus 1 over x. Here the x's cancel, I'm left with a 1. There nothing cancels, I'm left with a 5 over x. Now I'm going to plug infinity in for those two x's. I'm going to get 1 plus 1 over infinity over 1 plus 5 over infinity. And any fraction that has an integer in the numerator and infinity in the denominator is equal to 0. So this is going to be 1 plus 0 over 1 plus 0. Each of these pieces are 0. And that's going to be just 1, because 1 over 1. And for my answer for 16D, I'm going to say the horizontal asymptote, they all have an equation y equals, and this is going to be y equals to 1. So I'm going to graph that on my graph as well. So I'm going to find 1 on the y-axis and draw a dashed vertical line through it. I always draw asymptotes with dashed lines. Alright, the video is getting ready to hiccup. The next group of problems that we're going to have is to find the intervals where the graph is increasing, decreasing, and the maximums and minimums. Notice I'm getting lazy because I don't want to write the word increasing and decreasing. It's enough just to put an arrow up to mean increasing and an arrow down to be decreasing. And I'm not even writing relative for maximums and relatives for minimums. So this function, 16, was f of x equals x plus 1 over x plus 5. Because there's an x in the numerator, I'm not going to rewrite this to use the chain rule. it won't be that easy, wouldn't make it much easier. So I'm going to find the derivative. F prime of x is going to be the denominator x plus 5 times the derivative of the numerator, that's going to be the derivative of x plus 1, minus the numerator x plus 1 times the derivative of the denominator, which is the derivative of x plus 5, all over the denominator squared. The derivative of x plus 1 is just 1. The derivative of x plus 5 is just 1. So I can rewrite this as f prime of x equals to 1 times x plus 5 minus 1 times x plus 1 all over x plus 5 squared, just by putting the derivatives to the left of the parentheses. That's going to give me f prime of x equals x plus 5 minus x minus 1 over x plus 5 squared when I clear the parentheses. Now in the numerator, the x is going to cancel, and 5 minus 1 is 4. So I get f prime of x equals 4 over x plus 5 squared. That's the derivative, so now I can get into the point that I can get critical numbers. I get critical numbers of a fraction by taking the numerator and the denominator and setting them separately equal to 0. So I'll go 4 equal to 0, and x plus 5 squared equal to 0. The 4 equal to 0, because it doesn't have an x, doesn't give a solution. For the x plus 5 squared equal to 0, it's enough just to take the inside of the parentheses and set it equal to 0. And I'm going to get x equal to negative 5 for my critical number. So on a graph of a number line, I'm going to put negative infinity and positive infinity on the edges, negative 5 between them, and create my intervals from negative infinity to negative 5, and negative 5 to infinity. I need to pick numbers to plug into the first derivative. In this interval, I'm going to plug x equal to negative 6. This one, since it goes from negative to positive, I'm going to do x equal to 0. Now I need to find f prime of negative 6 and f prime of 0. I'm going to do both of those using the dy dx feature on my calculator. So that means I have to enter the original function on my calculator, graph it so I can do the dy dx part on it. So the original function I'll throw in. So y equals clear, it's parentheses x plus 1 divided by parentheses x plus 5. I'm just going to do zoom standard, and that's probably going to be good enough anyways for a graph. And now I'm going to go second calc, go down to value, dy dx. First one I'm going to type in is negative 6. And when I plug in negative 6, I get approximately 4. Because that's positive, in that interval, the graph is increasing. As I move from left to right, it's going up. Next, I'm going to do f prime of 0. So second calc, go down to number 6, dy dx, type in 0, and I get 0.16. It's also positive, so in that interval, the graph is increasing. You can see that it's increasing because it's going up on both intervals. As I move from left to right, the graph is going up. Has a break there at the vertical asymptote. So now I can answer the parts that I need to for E, F, and G. So it's increasing from negative infinity to negative 5, union negative 5 to infinity. It's never decreasing, it's only increasing. And because it doesn't change from increasing to decreasing or decreasing to increasing, you don't get a max, you don't get a min. I'm going to take that into consideration when I do my graph, but it's not really going to show up on my graph. Alright, so into the last part before I actually sketch the graph. So for I, J, and K, or H, I'm trying to find out where the graph is concave down. I am trying to find out where the graph is concave up. In J, I'm finding any inflection points. And to do those, I need to know the first derivative and the original function. The original function was f of x equals x plus 1 over x plus 5. The derivative was f prime of x equals 4 over x plus 5 squared. This one is a derivative of a fraction that doesn't have a letter in the numerator, so I'm going to rewrite it to use the chain rule. If there was a letter in the numerator, I'd use the quotient rule. So I'm going to rewrite this as f prime of x equals 4 times x plus 5 to the negative 2, and I'm going to use the chain rule. I'm going to go f double prime, which is second derivative, equals negative 2 times 4, leave myself some room, and then lower the exponent by 1 to negative 3. Inside where I left the room, I put the derivative of the contents of this parentheses. The derivative of x is 1, the derivative of 5 is 0, so I put a 1 there. Now I'm going to multiply these three numbers, put this back down to the denominator of a fraction to make its exponent positive. I'll get f double prime of x equals negative 8 over x plus 5 cubed. I'm going to get my critical numbers now. To get the critical numbers of a fraction, you separately take the numerator equal to 0 and the denominator equal to 0. Negative 8 can't equal to 0 because there isn't an x. For the x plus 5 cubed equal to 0, it's enough just to take x plus 5 equal to 0, and you're going to get x equal to negative 5. So now I'm going to go to my number line. On my number line, I'm going to plug negative infinity, positive infinity on the edges, negative 5 between them, get the same intervals, negative infinity to negative 5 and negative 5 to infinity. In each interval I need to pick a number. In this one I'm going to pick x equal to negative 6. This one I'm going to pick x equal to 0. And for both of them I need to plug a number into the second derivative. So here I have to do f double prime of negative 6, which is going to be negative 8 over negative 6 plus 5 cubed. I'll do that from the main screen on my calculator. And for this one, I'm going to go negative 8 over 0 plus 5 cubed. And I'm worried about the sign more so than the number. So first region here, I do second clear, negative 8 divided by parentheses negative 6 plus 5 up arrow 3. I get positive 8. So in this interval, the graph is concave up. So I get 8. Now for this one, I go negative 8 divided by 0 plus 5 up arrow 3, and I get negative 0.064. Because it's negative, the graph is concave down. So I'm done with that part. I'm going to get these into my answer. So the graph is concave up. I think I have these reversed. H is concave up. I is concave down. The graph is concave up between negative infinity and negative 5. It's concave down between negative 5 and infinity. There should be an inflection point because it changes concavity, but that's at x equal to negative 5. There's an asymptote at negative 5, so there won't be ever an inflection point across a vertical asymptote, so there's going to be no inflection point. So now I don't really have anything to add to my graph, but I need to make sure it shows everything it needs to show. Specifically, the things that it needs to show is that it's increasing from negative infinity to negative 5 and drawn to the asymptotes. It's increasing from negative 5 to infinity and drawn to the asymptotes. It's concave up between negative infinity and negative 5, and it's concave down between negative 5 and infinity. So if I just steal from my calculator now, it's going to work just perfectly. And again, if I didn't have a calculator to get a more accurate graph than I can get without a calculator, I'd have to find way more points. And that's because it'll take too long, and it's not any skill that we have to do. So this first region I'm going to copy here. Look at all this. It's drawn to this horizontal asymptote, and it goes concave up and increasing, and it's drawn to the vertical asymptote. So that's a perfect picture of something. It's increasing, it's concave up, it's drawn to the horizontal asymptote, it's drawn to the vertical asymptote. In the second region, I have to go through both the intercepts. I have to be increasing and concave down. So here, it goes through this intercept, it's off to the right, it's drawn to that horizontal asymptote, and then to the left, it's drawn to the vertical asymptote, and it stays concave down. So that region is increasing, goes through the intercepts, and it's concave down. and looks enough like that that I'm going to call that a perfect graph, and I'm not going to do more than that to get a graph. And that's all I expect you to do when you do your graphs, is more or less just make sure that your calculator graph says the same thing that your calculus says it should say. All right, so I'm going to do one more, and then I'm going to leave you short one again, just because 3 takes me a full hour to do. So we have 4 problems left on this video, then we'll jump into a part 3, and there's going to be a part 4 after that. For problems 17, 18, as well as 19 and 20, the concavity stuff is pretty ridiculous. The second derivative is pretty hard to compute, and it's really tough to do any sort of algebra with. So in 17, 18, 19, and 20, we're going to skip the concavity stuff. So we're going to skip H, finding the intervals where the graph is concave up, I, finding the intervals where the graph is concave down, and J, finding any inflection points. So we're flat out going to skip those for these 4 problems. And we're just going to do parts A through G, and along with K. So we're going to skip H, I, and J. And that only is for 17, 18, 19, 20. For 13, 14, 15, and 16, the concavity questions weren't ridiculous to do. So I'm going to do 18 with the hopes that you do 17 and 19. I'm not going to go through 20 just because of the whole length of time to do this. So part A of number 18 wants me to find the domain in the vertical asymptote. So eventually I'm going to write an answer as to what the domain is. I'll write it in words, and then I'll write it in interval notation, and then I'll write what the vertical asymptote is. And the vertical asymptote, or asymptotes, as there's going to be 2 of them in this case, just have the equation x equal to some number. So to find the domain and or the vertical asymptote for a fraction, you ignore the numerator, you solve the denominator equal to 0, and because this denominator has a square, I need to solve by factoring. The denominator, when you factor it, it factors into x plus 1 times x minus 6. Once I have it factored, I set the 2 factors equal to 0. When you set the factor of x plus 1 equal to 0, you get x equal to negative 1. And when you set x minus 6 equal to 0, you get x equal to 6. The algebra for finding the domain of a fraction for our class will give me the equations of any vertical asymptotes. It doesn't give me the domain written in a very nice way, but it gives me the numbers that need to be shoved into my domain. And for the domain part of this, I might say the domain is all real numbers except and in this case I'm accepting x equal negative 1 and positive 6. If you love having the domain in interval notation, to get the domain written in interval notation, you just simply write a negative and positive infinity on the edges of a number line. The numbers we're excluding from the domain on that number line along with the infinities, and then you'd create intervals. And these intervals, all with round parentheses, will form the interval way to write the domain. But I usually just write my domain in words. So this would be completely great for an answer to part 18a, at least the domain part. But you certainly would be absolutely okay if you said the domain contains the intervals negative infinity to negative 1, and then union negative 1 to 6, and union 6 to infinity. Have no problem with the interval notation. If you prefer it, that's completely fine. So this is going to show up on my graph. It's going to be the first feature I'm going to graph. So on my graph, I'm going to make my x and my y-axis. I need to show x equal to negative 1 and x equal to 6 as vertical asymptotes. And when I draw vertical asymptotes, I simply make dashed vertical lines through those values of x on the x-axis. So on my x-axis, or through my x-axis, I'm going to draw a vertical line through x equal to -1 and x equal to 6 to represent the breaks in the domain and the vertical asymptotes. They go hand in hand for us. Next thing I want to do is the intercepts, part B and part C, want me to find the x and the y-intercepts. And for a fraction, to do the x-intercepts, it's enough just to set the numerator equal to 0, or you can set the whole fraction equal to 0. So for 18 part B, when I go to do the x-intercepts, the easiest way to do it is just to set the numerator equal to 0. The harder but equivalent way to do it is to set the whole fraction equal to 0. So I could have just said 3 equal to 0, or I could take the whole fraction, 3 over x squared minus 5x minus 6 equal to 0. Those will give me the same answers. This one has a lot less work. In this version, just setting the numerator equal to 0, since there's no x in the equation, and this is a false statement, there's no solution to this equation, so there's going to be no x-intercepts. The graph's not going to cross the x-axis. If instead of just setting the numerator equal to 0, I tried to set the whole function equal to 0, then I'd have to rewrite the 0 as 0 over 1 and solve this by cross-multiplying. So I'd cross-multiply down and I'd cross-multiply up. When I cross-multiply down, I'd go 3 times 1. When I cross-multiply up, I'd go 0 times x squared minus 5x minus 6. On the left side, 3 times 1 is 3. On the right side, 0 times anything is 0. So you get the same 3 equal to 0, which is a lot more algebra. And similarly, because there's no x in this line and it's a false statement, there's no solution. So there's going to be no x-intercepts. So my answer to part B, there's going to be no x-intercepts. Moving on to C, the y-intercepts are fairly straightforward. To find the y-intercept, you just take 0 and plug it in for x. So for part C of 18, the function I'm dealing with, it should say f of x, and for whatever reason there's not an f of x written preceding the fraction like you have in 17. It should say f of x equals 3 over x squared minus 5x minus 6. And to find a y-intercept, I'm changing each of the x's to 0. So for the y-intercept of number 18, I'm just going to go f of 0 equals 3 divided by 0 squared minus 5 times 0 minus 6. And then the numerator's going to stay 3. The pieces with zeros in the denominators are just going to work their way down to 0. So I'm going to get 3 in the numerator, negative 6 in the denominator. That's 3 over negative 6. That reduces to 1 over negative 2. Looks odd to see the negative in the denominator, so I'm going to move the negative up to the numerator. I'm allowed to do that. And that's going to be the y-intercept for myself. At least that's the y part of the y-intercept. So my answer to part 18C likely should be a point. The y-coordinate of the y-intercept is negative 1/2. And always when you're finding intercepts, the letter that's not its name, its coordinate gets a 0. For the y-intercept, the x-coordinate gets a 0. So that point 0, negative 1/2 should show up on my graph. It's going to be beneath the x-axis, but on the y-axis. So here's negative 1 on the y-axis. And to plot the point 0, negative 1/2, I just simply make a dot on the y-axis between the origin and negative 1 on the y-axis, and I can mark that and call that my point. Alright, so that's a bit of grunge done, but not the real grunge for this. Part D is the horizontal asymptote. So for 18D, when I go to find my horizontal asymptote, for a fraction, it's enough when you're finding the horizontal asymptote just to find the limit as x goes to infinity of the function. So I'm going to find the limit as x goes to infinity, and our function is 3 over x squared minus 5x minus 6. When we're finding limits of fractions at infinity, we locate the highest power of x that occurs anywhere in the fraction. In this case, it's x squared. And we multiply every term in the problem by 1 over that power of x. So I'm multiplying by 1 over x squared because x squared is the highest power of x that occurs. In the numerator, nothing cancels. I can clean up the numerator by multiplying the 3 and the 1. That's going to give me 3 over x squared in the numerator. In the denominator, the first multiplication, the x squareds cancels out the fraction, leaves me with the 1. I leave the minus sign, and then the x from the 5x cancels with one of the x's from the x squared, leaves me a minus 5 times 1 over x. I multiply the minus 5 times 1 and get minus 5. I leave the x in the denominator, bring down this minus sign, and then 6 times 1 over x squared, there's nothing that cancels. I'll just multiply the 6 and the 1 and get minus 6 over x squared. Now I have nothing but x's in the denominators, and that makes it so I can plug infinity in. When I plug infinity in, I no longer write the word limit. So the numerator is going to be 3 over infinity squared. The denominator is 1 minus 5 over infinity minus 6 over infinity squared. And all the pieces that have an integer in the numerator and an infinity or some power of infinity in the denominator turn to 0. So the numerator is going to have a 0 in it from the 3 over infinity squared. The denominator is going to have a couple zeros in it from the minus 5 over infinity and minus 6 over infinity squared. If I simplify this, the numerator is just the number 0. The denominator, 1 minus 0 is 1. And any fraction with 0 in the numerator is equal to 0. This is going to be the equation of my horizontal asymptote. And the answer to problem 18D needs to be an equation of a horizontal line. So that equation should only have a y but not an x. And I'm going to write y equal to 0 for that equation because horizontal lines only have y's in their equations, not x's. And that's the value that's supposed to equal to. Y equal to 0 on my graph is going to show up on the x-axis. So I'm going to graph my horizontal asymptote on my graph for problem 18. This is kind of part 18K right here, the graph of function of problem 18. And I have my vertical asymptotes drawn, but I didn't really label them so well. And now I'm going to draw my horizontal asymptote, which is the horizontal line that just straddles the x-axis. So this is the horizontal asymptote of y equal to 0. I might have been nice if I said this is a vertical asymptote at x equal -1, and this is a vertical asymptote at x equal to 6. It's not such a big deal that I didn't physically label those. I kind of understand what those are. All right, so now we're to the algebra, the calculus part, to find the intervals where the function is increasing, decreasing, and any maximums and minimums. So in order to do problems, parts G, H, and R for problems E, the intervals where the graph is increasing, F, the intervals where the graph is decreasing, and G, any maximums and minimums, I'm going to need the first derivative. So I'm going to leave myself some room to do some work here. So my initial function, f of x, equals 3 over x squared minus 5x minus 6. I need to find its first derivative. It's a fraction, so I certainly could use the quotient rule to find my first derivative. There wouldn't be anything wrong with that. It probably would be clever if I rewrote this problem so it wasn't a fraction and used the chain rule. Anytime I have a fraction and there isn't an x in the numerator, rewriting the problem so that it's not a fraction and using the chain rule is probably the nicest, easiest way to take the derivative. But you absolutely could use the chain rule. In order to rewrite it, or the quotient rule, in order to rewrite it to use the chain rule, I have to think of the denominator as having a parentheses with an exponent of 1, and then I can move the denominator up to the numerator, make it so I don't have a fraction anymore, change the exponent from positive to negative. Now I'm going to use the chain rule. I'm going to take the exponent of -1, multiply it by the coefficient of 3. If that 3 was a 3x, then I'd be needing to use the product rule, and then this rewrite wouldn't help me at all. But exponent times the coefficient, leave myself some room, take the original parentheses, leave it the same, x squared minus 5x minus 6, lower the exponent to negative 2. Inside this parentheses, I'm going to take the derivative of each term inside the parentheses. The derivative of x squared is positive 2x. The derivative of minus 5x, because it's an x to the first power term, is just its coefficient of minus 5. The minus 6 is a constant, so its derivative is 0. Now I'm going to have minus 1 times 3 is minus 3 times 2x minus 5. And I'm going to move this x squared minus 5x minus 6 down to the denominator to make its exponent a positive 2. So that's a nice form, a nice factored reduced form of the first derivative. Now I'm going to find my critical numbers. And I find critical numbers for a fractions derivative by setting both the numerator and the denominator equal to 0. So I'm going to need to have my critical numbers before I can tell you where the graph is increasing or decreasing. So I'm going to set the numerator 3 times 2x minus 5 equal to 0. And I'm going to set the denominator x squared minus 5x minus 6 squared equal to 0. For the numerator, it's factored, so I split the factors up, set them separately equal to 0. I go negative 3 equal to 0, and 2x minus 5 equal to 0. The negative 3 equal to 0 doesn't have an x, so it doesn't give a solution, doesn't give a critical number. For the 2x minus 5 equal to 0, I'll add 5 to both sides and get 2x equal to 5. Divide both sides by 2 and get the critical number of x equal 5 halves. So that's one critical number. I'm going to get 2 more from this solution, this equation. When you have some quantity to any power set equal to 0, it's enough to drop the exponent and set the insides of the parentheses equal to 0. I could square root plus or minus square root to properly get rid of that exponent, but anytime the left-hand side of the equation has an exponent and the right side is 0, you can just take what's being raised to that power and set it equal to 0 to get your answers quickly. So I'm just going to solve x squared minus 5x minus 6 equal to 0. I'm going to solve that by factoring. Once I get it factored into x plus 1 times x minus 6, I'll take the factors and set them equal to 0. When I set the x plus 1 equal to 0, I get x equal to negative 1. When I set the x minus 6 equal to 0, I get x equal to 6. So that gives me 2 more values to put on my number line for the increasing and decreasing intervals. I'm going to create a number line that has negative infinity on the far left edge, positive infinity on the far right edge, and these critical numbers in order on my number line. I'm going to write negative 1 first, 5 halves, which is 2.5 second, and 6 third. That's going to create intervals. The intervals that are implied by my number line are the intervals from negative infinity to negative 1, the interval from negative 1 to positive 5 halves, the interval from positive 5 halves to 6, and the intervals from 6 to infinity. In each interval, I need to pick a test number and plug it into the first derivative. When I plug numbers into the first derivative for the increasing and decreasing, I'm only worried about the signs, and I use the dy dx feature on my calculator. In the far left interval, I'm going to pick x equal to negative 2, and eventually I'm going to find out what f prime of negative 2 is using the dy dx feature on my calculator. The second interval starts with a negative number, ends with a positive number. I can check 0 in that interval, so I will, and I'll find f prime of 0. The third interval goes from 5 halves, which is 2.5 to 6, so I need to pick a number in between 2.5 and 6. I'm going to pick 3 for that interval. And the last interval, I'm going to pick x equal to 7. The only reason I wrote this lower is because I didn't know if how much room I had to write what I needed to write. So I'm going to enter the function on my calculator, this f of x equals 3 over x squared minus 5x minus 6. So y equals, I already have it in there, but 3 divided by parentheses x squared minus 5x minus 6. I'm going to zoom standard. When I'm doing the increasing and decreasing intervals, if my window isn't sufficient for the final graph, it doesn't matter. It'll still get me a good increasing and decreasing answer. That window's not actually terrible. It might be suitable for my final answer. Maybe I'll have to tweak it a bit. But it's definitely enough to answer the increasing and decreasing parts that I'm worried about here. So my first interval, I'm going to plug -2 in by going second calc, going down to number 6, typing in -2, and I get 0.42. Because this is positive, in this interval, the graph is increasing. And above my number line, I'm going to put a little increasing arrow. In the next interval, I'm doing 0, so I go second calc, go down to number 6, dy dx, type the number 0 in, and I get rounds to 0.42 again. Again, I don't care so much the specific number that I get when I do this test. I just care whether it's positive or negative. If it's positive, in that interval, the graph is increasing. If it's negative, the graph is decreasing. This is another increasing interval. I'm going to draw an increasing interval here. And at x equal to -1, I don't get a maximum or a minimum because you have to have intervals with different directions next to each other. Two increasing intervals don't produce a maximum or a minimum. Next interval, I'm checking 3, so second calc, dy dx, type in 3, and I get -0.02. Again, I don't care so much about the 0.02, I just want the sign. That's important because in this interval I got a negative value. In that interval from 5/2 to 6, the graph is decreasing. And immediately when I put that decreasing arrow next to my increasing arrow, I can see I'm going to have a maximum, and the x value of the maximum is 5/2. Last interval, second calc, dy dx, plug my 7 in, and I get -0.42. Lots of 0.42s here. The fact that it's negative tells me in this interval the graph is decreasing again. So I write another decreasing arrow, and at 6 there isn't a maximum or minimum because you have to change directions into successive intervals to get a maximum or a minimum. So I'm about ready to answer most of problem 18E, most of the rest of what I need to do. For 18E, I'm going to say it's increasing in the intervals from -infinity to -1, and then again in the interval from -1 to +5/2. For 18F, I'm going to say the graph is decreasing in the interval from x equal to 5/2 to x equal to 6, and then again from 6 to infinity. For 18G, I need both the max and the min, and I know that there's a maximum and its x coordinate is 5/2. I don't know its y coordinate, so I can say there's a relative maximum of y equal to some number, which I need to figure out, which occurs when x equal to 5/2. And then I also can say for the relative minimum that there's none. So I almost have all of E, F, and G answered. The only thing that I don't have answered is the y coordinate of the maximum point. I like to get y coordinates by using my value screen, but in this case the value is not going to be nice enough for my answer. So if I did want to find the relative maximum and I wanted to find the y part of it, I could go second calc, hit enter on value, and type 5 divided by 2, and I get y equal to -0.24489 or -0.24. That's not suitable. I don't want a decimal answer, so I need to use the main screen of my calculator, not the value screen, to get this y value. My initial function is f of x equals 3 over x squared minus 5x minus 6. To find the y value that goes in my answer for the maximum, I have to change the x's to 5/2. And on my calculator, it's going to be a heck of a lot easier if I know that 5/2 is equal to 2.5. And if on my calculator to find the y coordinate of the maximum point, if I just go 3 over 2.55 times 2.5 minus 6 and make the decimal answer into a fraction, I will save myself a lot of grief with my calculator. So what I'm about to do next is finish up the y part of the maximum answer. I should get something that's equal to this negative 0.244898. Let me just write down a lot of decimals. So when I go to my main screen and do the computation, 3 divided by parentheses 2.5 squared minus 5 parentheses 2.5 minus 6. When I do this computation, I should get negative 0.244898 because that's the decimal equivalent of the y-coordinate for the maximum. And I get exactly that number. Let me math and enter twice to make it into a fraction. So I get negative 12 over 49 for the y-coordinate of the maximum point. And I can say there's a relative maximum of y equals negative 12 over 49, which occurs when x equals 5/2. This shows up on my graph as a point. So when I pull out my graph, this as a point is going to be the point x equal to 5/2, y equal to negative 12 over 49. That's what I'm going to write. But when I go to graph it, I think x equals to positive 2.5, y equals to negative 0.24, which is like negative 1/4. So I'm going to graph that point. 2.5 on the x-axis is about there, and the negative 0.25 is slightly higher than negative 1/2. So that point is going to be about there. I'm going to call that the point 5/2, comma, negative 12 over 49. I'm not doing the concavity stuff, so I'm ready to jump to my graph because I've done all the parts A, B, C, D, E, F, and G. Normally I do H, I, and J for the concavity, but I'm skipping that, and I'm going to sketching the graph. The only features I really need to show on my graph are the y-intercept. There is no x-intercept. The maximum point, the asymptotes, I have all those drawn in. So I'm ready to borrow a graph from my calculator. I better make sure that my graph is increasing from negative infinity to negative 1, which means this whole part of the graph is going to be increasing. And it's also increasing from negative 1 to 5/2, which is kind of the middle part between, it's between this dashed line and that point right there. So it's increasing here, increasing to there. And then it's going to start decreasing. It's decreasing from 5/2 to 6. That's decreasing from this point to this vertical line. And it's decreasing from 6 to infinity, which is this whole side. I'm going to borrow a graph from my calculator. I already have a graph on my calculator. I don't know that I like that window perfectly well. What I'm going to do, because I want to see with a little more detail what's going on in here, I'm just going to make my y's a little bit smaller. Maybe make my y's go from maybe like negative 4 to 4, just because I think it's going to give me a better image of what's going on between the two vertical asymptotes. And when I do that, I don't know that it's significantly better, but it's a little bit better. So in the kind of left panel of my graph, I'm going to draw a graph that has to be increasing. It looks like it's concave up, but I didn't know that with concavity. And there aren't any specific points it has to go through. There's no x or y intercepts plotted in there, but it needs to be drawn to the asymptotes. So it's going to go up towards the vertical asymptote, not cross nor touch the vertical asymptote, and off to the left, it's going to be drawn to the x-axis, which is the horizontal asymptote. So that's kind of the first quadrant, not drawn as well as my calculator drew it. I probably should have drawn it more like that, but I didn't because the calculator is blocking my ability to make that curve. But something that resembles that. In the middle quadrant, I need to have a graph that's going towards this vertical asymptote. It increases constantly. It goes through the y-intercept. There is no x-intercept. It goes through the maximum point. Looks like it's all concave down there, and I would have known that if I did the second derivative test completely. After it gets to the maximum point, it starts to decrease, and it gets drawn to this vertical asymptote. In the far quadrant, I'm just going to draw a graph that's decreasing, and there's no points to go through, but it has to go towards the vertical asymptote and towards the horizontal asymptote. That looks like a good enough graph. If I want to get the vertical asymptotes drawn on my graph, it's a trick to do. So my graph doesn't show the vertical asymptotes, and this vertical asymptote is x equal to -1. That's x equal to -6. If on my calculator for this, if I entered y2 equals 1,000 times x plus 1, I could get something that looks like a vertical asymptote. My calculator can't draw vertical asymptotes because they're not functions, and it can only draw functions. This would simulate that. So if I drew on my calculator, went to y equals and typed 1,000 times x plus 1 and added that to my graph, you'll see that what I have for my vertical asymptote drawn as a solid as opposed to a dashed line. Similarly, if I want my calculator to show that vertical asymptote, I'd probably enter in y3 1,000 times x minus 6, kind of moving the number over. So if I did y equals 1,000 times parentheses x minus 6 and graphed it, I'd get this second vertical asymptote, which I already drew in. So now the graph that I have on my calculator looks more like my graph on my screen here, and I feel good about what I have. Again, I'm not looking for complete accuracy in your graphs, just something that does what it's supposed to do. Increases where it's supposed to increase, decreases where it's supposed to decrease, goes through maximum points, goes through any intercepts, and for the concavity part, has the right concavity once we've figured out the concavity, but we're not doing the concavity for 17, 18, 19, and 20. So I'm going to skip doing number 20. You should do 17 and 18, and then 19 and 20, and I seem to have lost my 19 and 20. So I don't know if I can find those anymore, but I had them up on the screen earlier, so you need to find out what problem 19 is, and do both problem 17 and 19. Oh, here it is. So your problem 17 and 19 are right there. So give those both a try, and for those, skip the concavity questions. So that will be the end of this video. There's going to be 2 more parts. The part 3 that we're doing next is going to have E functions, and then part 4 is going to have ln functions.